6,192 degrees Fahrenheit, is the staggering temperature at which this metal finally begins to succumb to heat. Why does the modern world depend so heavily on a substance that remains solid while others evaporate? At temperatures where steel transforms into a volatile liquid and gold vanishes into the atmosphere as vapor, this element maintains its structural integrity without even exhibiting a red glow. Without its presence, aircraft engines would fail mid-flight, urban power grids would descend into darkness, and the industrial machinery responsible for shaping our civilization would grind to a halt. But this is just the beginning. Engineers and nations across the globe compete fiercely for every single gram of this rare material. It only looks obvious that we must mine it from the earth, but in reality, the industry relies on a hidden cycle of transformation. Nearly 40% of the metal currently supporting global infrastructure has already reached the end of its functional life and been resurrected through complex reprocessing. Everything only gets more complicated as we examine the properties of element number 74. One can notice how its extreme density and thermal resistance make it irreplaceable in high-stress environments. The process of analyzing its origins reveals a narrative of resilience and chemical stubbornness. It is visible how the metal resists destruction, moving from one industrial application to another in an endless loop of melting and solidification. The story of tungsten unfolds through its unique atomic structure and its role as the backbone of heavy industry. The metal transitions from a raw state into a refined component, ensuring the stability of the world's most critical systems. From here, the exploration moves into the specific technical mechanisms that allow such a heat-resistant material to be captured and utilized. This concludes the introduction to the fundamental properties of the element. 3,422 degrees Celsius is the specific thermal threshold required to reach the melting point of tungsten. Why is such an extreme temperature necessary for a single metallic element? It seems simple to compare industrial heat to everyday fire, but this level of thermal energy is sufficient to vaporize the majority of other known materials instantaneously upon contact. The heat required to liquefy this metal is physically comparable to the intensity found on the surface of a star. But heat resistance only marks the initial stage of its mechanical superiority. One can notice how this metal maintains the highest tensile strength among all pure elements, even when subjected to temperatures of 3,000 degrees Fahrenheit. At this point, structural steel would have already lost all its physical integrity and load-bearing capacity. The equipment measuring these parameters records no deformation, as the metal remains incredibly dense and hard under extreme stress. It only looks obvious that a material would be heavy, but holding a small cube of this substance in the palm of a hand creates a sensory contradiction. The brain struggles to process how such a compact volume can possess such immense weight. This extreme density makes the material entirely irreplaceable in high-stress environments. It does not deform, it does not yield, and it does not fail in conditions where any other known substance would be destroyed in mere seconds. The metal serves as the definitive physical barrier between the structures humanity intends to build and the constraints that nature imposes on existence. But this is just the beginning. Everything only gets more complicated when the focus shifts from the properties of the metal to its extraction. If this element is capable of withstanding the most intense heat imaginable, the effort required to extract it from the cold depths of the planet represents a brutal mechanical battle. Tungsten is never found in a pure state within the natural environment. It is one of the rarest elements existing in the Earth's crust, concealed deep within layers of hard rock formations, known specifically as wolframite and scheelite. At first glance, the planet seems vast, but in reality, the global reserves deemed economically viable for mining are estimated at only approximately 3,500,000 tons. The process is only gaining momentum as the rarity of the resource dictates global strategy. This total volume is almost negligible when compared to the hundreds of millions of tons of iron or aluminum produced annually. Consequently, every discovered deposit is classified as a critical strategic treasure. To secure these mineral assets, nations including China, Russia, and Canada operate massive mining complexes that span kilometers. Geologists utilize advanced satellite and seismic technology to locate the specific veins where the ore is concentrated. Transition to the next level occurs when raw physical power takes over the operation. Industrial explosives are detonated to shatter solid rock formations, while heavy drilling rigs penetrate the Earth's crust with constant rotation. It is a dangerous and relentless industrial labor. One can notice how colossal dump trucks, capable of hauling thousands of tons of ore every single day, ascend from the depths of open-pit mines. The equipment moves at a steady pace as hydraulics hiss under the massive weight of the raw stone. Every individual rock extracted from the pit represents a minor victory in a complex global logistics war. The raw material is now ready to move toward the primary crushing stations for further refinement. 3,000 degrees. This is the thermal threshold required to begin the chemical transformation of raw ore into an advanced industrial material. Why must such a complex chemical labyrinth be navigated to extract metal from common rock? At first glance, the mineral appears to be merely a dirty stone, but within its structure lies the potential for space-grade applications. Without a series of aggressive interventions, the valuable crystals would remain trapped inside the inert geological matrix, making the metal unreachable. Giant industrial crushers and heavy mills initiate the process by executing the total destruction of the rock. One can notice how the equipment gradually pulverizes the large boulders until they are reduced to a fine, uniform powder. This mechanical breakdown is necessary to physically liberate the high-value crystals from the surrounding waste. The process is only gaining momentum. Engineers utilize the physical laws of gravity and the force of powerful magnets to separate the treasure from the discarded debris. This stage produces a refined concentrate, though it has not yet reached the state of high-purity metal. Everything only gets more complicated. The material then enters a sequence of complex chemical reactors, where it undergoes immersion in acidic baths and exposure to high-temperature furnaces. The primary objective is the total removal of all foreign impurities at an atomic level. It is visible how the substance is roasted until it transforms into tungsten oxide, a specific powder that serves as the fundamental base for all subsequent production steps. This is a process of dismantling nature atom by atom to allow for a complete reconstruction of the material. Now the transition to the next level begins within the heart of the metallurgical transformation. To become a metal, the oxide must be stripped of its oxygen molecules. This critical reaction occurs inside specialized furnaces, maintained with a hydrogen atmosphere and heated to temperatures exceeding 3,000 degrees. One can notice the slow change in the material as it emerges as a fine gray powder consisting of pure tungsten. But this is just the beginning of the technical challenge. It seems simple to melt a metal once it has been purified, but in reality, tungsten possesses an extraordinarily high melting point. This physical characteristic makes it nearly impossible to melt the substance using standard industrial methods. The process concludes this phase, opening the road to formation. 6,170 degrees Fahrenheit is the extreme melting point of tungsten, a temperature so high that it defies the limits of conventional metallurgy. Why is it impossible to cast this metal using traditional foundry methods? At such a thermal threshold, every known crucible or mold would disintegrate or vaporize long before the metal reached a liquid state. But this is just the beginning. Engineers utilize the process of sintering to bypass the limitations of the liquid phase. It seems simple at first glance, but in reality, it requires a delicate balance of physical force and thermal energy. High-precision hydraulic presses subject the fine metallic powder to crushing pressures, compacting the grains into a dense and specific geometric form. Heat is applied gradually until the material reaches a state just below its melting point. One can notice how the 1,000 meters of solid granite and dense rock are easily breached by tools reinforced with this specific material. Why is such extreme hardness necessary for industrial progress? It would seem that standard hardened steel might suffice for deep earth exploration. But without the unique physical properties of tungsten, modern energy extraction and manufacturing sectors would face a total halt in production. This metal also functions as a master of calculated destruction. Tens of tons of kinetic force are concentrated when tungsten is utilized within the military sector for armor-piercing projectiles. One can notice how the absurd density of the element allows a projectile to maintain its structural integrity upon impact at high velocities. It does not deform against the target, but instead pierces through multiple layers of heavy steel plating with devastating efficacy. This process involves concentrating a colossal amount of energy onto a single minuscule point of contact. Everything only gets more complicated when considering its role in non-destructive fields. Tungsten acts as a silent guardian within the most delicate medical technologies currently in operation. In this field, its high density serves a constructive purpose within X-ray tubes and specialized radiation shielding. At first glance, lead might seem the obvious choice for blocking waves, but in reality, tungsten provides a non-toxic alternative that blocks radiation effectively and safely. The equipment gradually ensures the protection of both medical staff and patients during diagnostic procedures. The process is only gaining momentum as the metal enters the aerospace industry. One can notice how tungsten alloys operate reliably inside the thermal hell of jet engine turbines. At these extreme coordinates, the atmospheric heat would cause other conventional metals to lose their structural stability or melt entirely. The camera glides along the precision-engineered components that must withstand these constant thermal cycles. But this is just the beginning of its mechanical utility. Its concentrated mass makes it the ideal material for balancing complex high-speed machinery. Engineers integrate tungsten weights into Formula One racing cars, specialized instrumentation, and commercial aircraft to fine-tune the center of gravity. It is visible how the metal remains stable even under the influence of extreme centrifugal forces and vibrations. The heavy components allow for precise weight distribution without requiring excessive volume. The material reaches the required balance standards, transitioning into a calm state of functional operation. Thus, the tungsten completes its essential role across these diverse technical landscapes. 100% density allows this metal to serve as the ideal material for counterweights, occupying the smallest possible physical volume while providing critical stability to complex machinery. Why is its presence so vital in the field of electronics? The answer lies in its ability to function where heat becomes unbearable for any other element. One can notice the thin filaments inside incandescent lamps and high-performance components glowing as they conduct electricity without melting. The process is only gaining momentum. Limited reserves and a voracious global demand create a constant pressure on the supply chain. At first glance, the extraction of such a rare resource might seem unsustainable, but in reality, the industry relies on the most efficient recycling system on the planet. Tungsten functions as a zombie metal, possessing the unique ability to return from the dead through advanced reprocessing. Broken drill bits and worn-out industrial tools are never discarded as waste, but are instead treated as high-value technical resources. 40% of the total global consumption of tungsten is currently derived from recycled materials. One can notice how factories collect these degraded components and systematically convert them back into a state of pure powder. This refined substance is then prepared for pressing into new shapes, ready for immediate industrial application once again. But this is just the beginning. This closed-loop cycle proves significantly more cost-effective and environmentally clean than the traditional method of detonating mountains to extract raw ore from the earth. Carbon emissions and landscape disruption are reduced as the material moves through this infinite loop. This ensures that the global supply of this vital resource remains stable despite the scarcity of natural deposits. It is visible how the metal lays in an even layer during the powdering stage, marking the transition to its next life cycle. Tungsten serves as the invisible backbone of the modern technological era. It acts as the physical barrier, separating achievable engineering from the impossible. The equipment gradually reaches new heights and greater depths because of this element's extreme thermal and mechanical properties. It enables aircraft to fly higher and industrial drills to penetrate deeper into the crust of the planet. From here, the transformation moves to the next phase of processing as the metal continues to support the infrastructure of safety and progress. Thus ends one of the key stages of exploring the life cycle of the world's toughest materials. 60 million kilometers is the total length of electrical cables that encircle our planet at this very second. This is a quantity of wire sufficient to wrap around the Earth 1005. 3 stories, exactly the height reached by hydraulic excavators that move across the rubble in the quarry. This massive scale is necessary because to reach the valuable ore, engineers must first move entire mountains. Why do they utilize such destructive force at the beginning of the cycle? It seems that manual extraction would be impossible given the geological density of the terrain. Only controlled explosions can break the resistance of the Earth, fracturing thousands of tons of rock in a single calculated moment. Industrial drills penetrate the solid rock with precision, creating dozens of deep boreholes that are subsequently filled with detonating charges. Once the signal is given, the Earth literally opens up. The explosives detonate with a millisecond delay, and one can notice how thousands of tons of rock are fractured in an instant, releasing a thick cloud of dust that gradually covers the entire horizon. This is the brute force required to release the copper and the aluminum from a geological sleep that has lasted for millions of years. But this is just the beginning. Excavaderas' hydraulic machines advance over the debris with the hiss of powerful pistons. Their buckets are so large that they could lift a passenger car without any perceptible effort from the hydraulic system. The equipment feeds a fleet of mining trucks that function as massive mechanical transporters. Each of these vehicles carries 300 tons of ore in a single trip across the quarry floor. If a person stood next to one of these tires, it would be twice as high as their own head. The process is only gaining momentum. These steel giants roar along the mine roads, transporting the raw earth toward the primary crushing stations. One can notice how the suspension compresses under the immense weight of the cargo. Inside the station, stones the size of large sofas are crushed as if they were simple cubes of sugar. The heavy rollers rotate ceaselessly, reducing the boulders to much smaller fragments that are ready to be sent to the refineries. It only looks obvious that the work is nearly finished, but in reality, all that has been gathered so far is dirty stone and fine dust. Transition to the next level. To transform this raw dirt into a perfect conductor of energy, the material must pass through the next stage of chemical and physical refinement. The raw material leaves the crushing station, transitioning into a calm stage of transport. 1,742 degrees Fahrenheit is the intense thermal threshold where solid mineral matter begins its final transformation into liquid metal. The mechanical power previously witnessed in the mines gives way to the extreme environment of the smelting facility. Why is such a massive investment of thermal energy required at this stage? The raw, impure ore entering the industrial furnaces possesses chemical bonds that only temperatures of 950 degrees Celsius can dismantle. But this is just the beginning. The equipment gradually initiates a violent chemical battle within the aluminum production cycle. Material extracted from bauxite is submerged into specialized electrolytic reduction cells. Colossal electric currents, possessing an intensity capable of instantly destroying any standard domestic electrical system, tear through the molecular structures of the ore. It only looks obvious that heat alone would suffice, but in reality, the combination of electrical force and thermal energy is what forces the rock to surrender. Everything only gets more complicated as the reaction stabilizes. One can notice how the pure aluminum separates from the waste material under this unbearable heat. It drips steadily to the bottom of the containment tank, appearing as a brilliant silver liquid. It is visible how the molten metal forms a dense stream at the base of the cell. The process is only gaining momentum. This river of liquid metal remains extremely hazardous while maintaining a perfectly smooth, reflective surface during its collection. For copper, the industrial requirements are even more rigorous and demanding. The transition to the next level involves a different set of chemical stressors. Copper undergoes a series of purification stages that exceed the complexity of aluminum reduction. The material moves through the system as the thermal sensors monitor every degree of fluctuation. From here, the transformation moves to the next phase of processing. 99.9% is the absolute threshold of purity that the metal must reach as electricity functions like a microscopic filter to strip away every individual atom of contamination. Why is such extreme chemical precision required for the material at this stage? One might assume a minor fraction of impurity would be negligible in such a massive volume. But in reality, even a single microscopic particle of foreign matter could trigger a fatal short circuit hundreds of kilometers away once the line is operational. The process is only gaining momentum. Liquid metal, now purified and glowing with an incandescent light, is poured into heavy steel molds. One can notice how the molten stream fills the containers, but the cooling process cannot be left to chance. Automated forced cooling systems immediately begin to spray high-pressure water against the exterior of the mold. This causes the outer shell of the metal to solidify instantly through thermal shock, while the inner core remains hot and malleable. It is visible how the equipment gradually manages the temperature gradient to prevent internal structural flaws. Transition to the next level. Solid ingots emerge as massive bars of metal that radiate an intense orange and red glow into the surrounding workspace. It seems simple to view these as finished products, but a solid block of metal cannot yet transport electricity into a residential home. Because of this, the material must undergo a radical physical transformation where it will be crushed and stretched far beyond its current physical dimensions. The ingot, still vibrating with stored thermal energy, moves steadily toward the rolling line. Rolling mills consisting of hardened steel cylinders apply a mechanical force of several hundred tons to the surface. Everything only gets more complicated as the metal passes between the rollers. The camera glides along the machinery as the massive ingot is forced through the narrowing gap, and the material emits a high-pitched mechanical scream under the immense pressure. Each pass through the rolling stand reduces the thickness while extending the length of the metal, fundamentally altering its crystalline structure. The metal is ready for casting, where it will take shape. 8 millimeters is the diameter the metal reaches after it is relentlessly crushed and elongated into a long rod or rebar. This thickness remains far too substantial for the production of the delicate strands required for modern cable construction. Consequently, the material enters the wire drawing phase, a stage where engineering precision transitions to a microscopic scale. The process is only gaining momentum. Automated systems pull the metal rods through a sequential series of increasingly narrow apertures known as dies. These components are frequently constructed from industrial diamonds to withstand the immense friction. One can notice how the equipment gradually narrows the material as the speed of the line reaches dozens of kilometers per hour. This is a sequence of controlled violence where the rod is physically forced to become longer, thinner, and perfectly cylindrical. Why is such extreme speed maintained during the drawing process? The velocity ensures the metal remains under constant, even tension. From a thick industrial rod, the material transforms into a filament that is eventually finer than a single strand of human hair. High-precision lasers monitor every inch of the wire in real time. It is visible how the camera glides along the gleaming surface while the sensors detect the slightest deviations. If the diameter fluctuates by even 1/1000th of an inch, the laser identifies the error, and the system executes an instantaneous adjustment. The result is a brilliant wire with a surface as smooth as a mirror, but this is just the beginning of the material's final transformation. A hidden structural problem exists within the metal at this stage. After the rod has been pulled, stretched, and compressed through industrial diamonds, the internal crystal lattice is under extreme stress. The metal has become rigid and brittle to the point of structural instability. It only looks obvious that the wire is strong, but in reality, any attempt to bend it would cause it to shatter like glass. It requires a form of thermal therapy to restore its mechanical properties. To heal the internal structure, the wire is moved into specialized annealing chambers. These sealed furnaces act as high-technology environments designed to revitalize the exhausted metal through controlled heat. Within these pressurized vessels, the molecular arrangement begins to realign. Everything only gets more complicated as the thermal cycles must be calibrated with absolute precision to ensure the wire regains its flexibility. The material enters the heat treatment stage, where the internal tension will finally be released. 600 degrees Fahrenheit is the specific thermal threshold reached as the metal passes through the heating zone. Why is such a precise temperature maintained if it is not high enough to melt the wire? The answer lies in the atomic architecture of the material. At this exact level of heat, the atoms within the copper and aluminum begin to relax and reorganize. But this is just the beginning. The crystalline structure of the metal, which became distorted and severely stretched during the intense drawing process, undergoes a complete realignment. One can notice how the internal tension simply evaporates as the lattice stabilizes. The equipment gradually relieves the physical stress accumulated in the fibers. It only looks obvious that the wire remains the same because its external appearance does not alter as it exits the chamber. In reality, the material has changed fundamentally. Before this stage, the wire was brittle and prone to snapping. Now, it is transformed into a soft and exceptionally flexible conductor. It is visible how the metal can be bent, twisted, or coiled without the slightest risk of structural failure. The rigidity disappears entirely. This invisible transformation acts as a thermal sigh of relief, ensuring the metal can withstand the mechanical demands of installation. Without this specific stage of annealing, no electrical cable in the world would function. Everything only gets more complicated. The process is only gaining momentum as we transition to the next level of production. Stranding represents one of the most technically hypnotic moments in the entire industrial chain. A single thin wire remains inherently fragile and limited in its application. However, if dozens of these filaments are united, they create a metallic rope of incredible mechanical strength. It seems like a simple process of bundling, but in reality, it is a feat of complex engineering and synchronization. One can notice the scale of the machinery, which occupies a space equivalent to a large train car. It carries hundreds of heavy bobbins loaded with gleaming wire. When the drive system activates, the entire assembly functions like a high-speed mechanical ballet. The massive rotating body of the machine, known as the cage, begins its rapid revolutions. The bobbins move in perfect circles, creating a silver vortex in the air as they spin. The individual wires are pulled with constant force toward a central point called the nose of the machine. There, the filaments are twisted over one another with absolute geometric precision. But this is not the limit. Engineers must calculate the exact angle of this helical twist to ensure structural integrity. If the twist is too tight, the resulting cable becomes excessively rigid and consumes an unnecessary volume of precious metal. Conversely, if the winding is too loose, the entire cable will unravel and lose its shape during the installation process. Everything happens in a blur of synchronized movement. The equipment generates a constant and rhythmic hum that fills the shop floor. High-precision sensors monitor the tension of every individual strand simultaneously. It is visible how the automated systems react to the slightest deviation. If a single wire, even one thinner than a human hair, happens to break in the middle of this mechanical hurricane, the entire machine stops in a fraction of a second. Perfection is the only acceptable output for the system. The finished strand emerges from the nose of the machine as a unified, powerful conductor. The metal is ready to move to the next processing phase without haste. One unified conductor emerges on the other side, no longer appearing as a mere collection of loose wires. Why must these individual strands be bound so tightly into a single core? This configuration ensures the component is as flexible as a heavy rope, while remaining as durable as a solid steel bar, capable of carrying the massive electrical currents that sustain modern existence. But at this specific stage, the raw conductor remains a lethal hazard. A single touch during operation would result in an immediate and fatal end for anyone in contact with the metal. It requires a structural armor to become functional and safe. Now, the principles of metallurgy give way to the complex science of industrial chemistry. The camera glides along as the bare metal conductor enters the extrusion line to receive its protective skin, known as insulation. Inside massive silver silos, tens of tons of small plastic granules, consisting of polyvinyl chloride or specialized polyethylene, remain in wait. These granules resemble tiny beads, appearing either perfectly white or transparent in their raw form. Vacuum systems suck these particles into a machine that functions as a giant high-powered thermal injection system. One can notice how the plastic is heated until it transforms into a viscous and completely homogeneous paste. The process is only gaining momentum. The metal wire passes through the precise center of a hardened steel crosshead, while the molten plastic is injected with force around its circumference. It seems simple, much like casing a sausage, but in reality, this operation requires a precision measured in micrometers. The plastic layer must be perfectly concentric relative to the core. If the insulation is even slightly thinner on one side than the other, electricity can escape through that weak point, leading to catastrophic fires or system failures. Immediately after the hot plastic contacts the metal, the entire cable plunges into a long trough filled with cold water. The thermal shock is instantaneous. The plastic hardens in a matter of seconds, locking its circular shape into a permanent state. But for larger cables, such as those buried beneath city streets, a single layer of protection is not sufficient. Everything only gets more complicated as additional protective barriers are applied. These include thick sheaths, resistant to corrosive chemicals, industrial oils, and even the gnawing of subterranean rodents. Certain submarine cables receive extra armors of galvanized steel to withstand the crushing pressure of the deep ocean floor. The final result is a product that appears virtually indestructible to the eye. Does the material truly possess the strength required for decades of service? The manufacturing facility will not rely on luck or assumptions. It will systematically attempt to destroy the product. Before a single meter of cable is permitted to leave the factory, it must survive the high-stress environment of the quality control laboratory. The stakes at this stage are exceptionally high. A failure in this cable does not merely result in a darkened room. It could mean a hospital losing critical power or a fire erupting in a high-rise building. At first glance, the laboratory looks like a place of quiet observation, but in reality, it is a chamber of controlled destruction. First comes the high-voltage electrical test. A voltage significantly higher than what the cable will encounter in real-world applications is fired through the conductor. Engineers monitor sensors for any sign of leakage or any structural weakness within the insulation layer. The process is similar to attempting to burst a balloon with high air pressure. If the cable possesses a microscopic weak point, it will explode here, within the containment of the laboratory. It gets more complex further on. Mechanical testing follows the electrical trials. Heavy machines stretch the cable to its absolute breaking point to ensure the metal and plastic do not delaminate or separate under tension. Samples of the finished cable are placed inside specialized fire chambers to observe if the insulation can resist intense flames or if the material fails under thermal stress. The material is ready to move to the next processing phase without haste. 60 million kilometers of cables are produced annually to sustain the modern world. Why must these conductors undergo such rigorous climate simulations? It only looks obvious that a cable should function in any environment, but in reality, extreme cold can cause the protective insulation to shatter like glass. To prevent this, every batch is subjected to freezing temperatures to ensure they do not crack during a harsh winter. Lasers scan the surface of the moving line in search of microscopic imperfections that remain invisible to the human eye. The equipment gradually reveals the internal structure as X-rays look through the thick plastic coating. This process ensures that the metal core remains perfectly centered within its protective sleeve. Only the cable that survives this gauntlet of inspections receives the official stamp of approval. But this is just the beginning of the logistics phase. The finished product is wound onto massive spools made of treated wood or heavy steel. One can notice how the automated winding arm layers the cable with mechanical precision. Each spool is weighed on industrial scales, labeled with digital tracking codes, and prepared for immediate transport. They are stacked in vast storage yards, resembling giant coins left behind by a civilization of titans. It is visible how these reels wait in rows before being unrolled into deep trenches, mounted on utility poles, or hidden behind walls across the globe. Transition to the next level. $200 billion is the annual value of this global industry. Look at the wall of a room right now. That hidden wire is far more than a simple combination of plastic and metal. It is a technical survivor. At first glance, it is a mundane object, but in reality, its journey began with a calculated explosion in a copper mine. It was subsequently melted in a chemical furnace, stretched through the microscopic holes of industrial diamonds, and cured by intense heat. The metal was braided in a high-speed mechanical vortex and tested with both open flame and high-voltage electricity. Everything only gets more complicated when considering its scale. These cables serve as the invisible arteries of modern civilization. Without their constant function, the energy and data flow of entire cities would cease in a single second. The process is only gaining momentum as infrastructure expands. The camera glides along the intricate network of wires that make a simple light switch function. It represents one of the most underestimated pieces of engineering in human history. Every small wire carries the legacy of a massive industrial saga. 2023 was the year farmers in the Nevada desert performed an action that appeared to be financial suicide. They covered their fertile acreage with thousands of tons of pure salt. Neighbors viewed the act as total madness. Experts initially claimed the soil had been rendered dead. However, this calculated technical maneuver did not destroy the farm. In just one growing season, the application of minerals transformed a sterile desert into a productive mine. The land began to yield a specific resource that the industry had previously overlooked in such environments. The process concludes this phase, opening the road to a new discovery. 100 degrees Fahrenheit is a standard temperature in the Nevada desert, where the sun does not merely shine, but hammers the earth into a hard, impenetrable crust. This environment functions as an open-air furnace, forcing a constant war against the physical elements of the landscape. Within this volatile setting, The survival of a million-dollar industry depends entirely on the destruction of the soil. Why would the intentional disruption of the earth be the only way to save a massive agricultural sector? Because beneath the surface of these parched fields lies a biological challenge that traditional technology could not solve for decades. Alfalfa may appear to be simple greenery at first glance, but in reality, this plant is an impenetrable biological fortress. It hides a mechanical secret within every small purple flower that has frustrated engineering and agriculture for generations. One can notice how the petals of the alfalfa flower conceal a reproductive column held under extreme physical tension. This mechanism functions exactly like a compressed steel spring or the cocked trigger of a firearm, waiting for a specific physical stimulus to release its stored energy. For the plant to produce the seeds that represent the farmer's primary profit, this internal trigger must be physically tripped. But this is just the beginning. When an insect lands to access the nectar, the defense mechanism detonates with a millisecond delay. The column strikes the visiting insect with a violent and surprising force. For a standard honeybee, this mechanical blow is a physical deterrent that alters its behavior. It is visible how the bees eventually learn to navigate the flower differently to avoid the impact. It only looks obvious that the bees would continue their work, but in reality, they begin to cheat the system. They extract the nectar from the side of the bloom to bypass the trigger entirely. The process is only gaining momentum toward a crisis at this stage. Because the bees avoid the mechanical strike, the flowers remain unpollinated despite the activity in the field. Consequently, a field can remain a deep, beautiful purple while failing entirely to produce the necessary crop yield. The industry faces a total collapse of production because the biological machines, the bees, refuse to trigger the plant's mechanical sensors. This tension between biology and industry is what makes the intervention in the soil a technical necessity for survival. The next stage of the process requires a complete shift in how the environment is managed to force the mechanical release of the alfalfa's potential. No seeds develop within the bloom without the trigger of a strike. Why does the lack of a seed lead to a complete collapse of profit? One might notice how the economic yields of alfalfa farms were slipping away like dry sand through an open hand. Without this fundamental reproductive cycle, agriculture becomes a sinkhole for capital. Until 2023, the industrial situation remained critical as farms effectively bled currency while pouring fortunes into irrigation and chemical fertilizers for crops that refuse to reproduce. At first glance, the problem seemed unsolvable by modern standards. The soil was gradually accumulating salt, while production costs climbed to levels that were physically and financially unsustainable. Human technology, equipped with high-powered tractors and complex synthetic chemistry, found itself defeated by the mechanical stubbornness of a single small flower. It only looks obvious that a machine could solve this, but in reality, every modern intervention failed one after another. This state of despair demanded an unconventional shift in perspective, or perhaps a calculated return to historical data. The solution to this multi-million-dollar industrial impasse did not originate in a high-tech laboratory. Instead, Dr. Clara Martinez discovered a vital clue within the dusty archive rooms of a university, hidden among forgotten papers from the 1970s. She identified a technical drawing created by an engineer whose work had been overlooked by contemporary history. The subject of this research was the Nomia melanderi, commonly referred to in technical circles as the alkali bee. The process is only gaining momentum. This organism bears no resemblance to the social insects found in commercial hives. One can notice how it exists without a queen, produces no honey for human consumption, and functions as a solitary underground laborer. Old records revealed that this insect acted as a perfect master key for the mechanical lock of the alfalfa flower. Evolution had engineered this creature with the exact physical weight and structural resilience required to activate the floral trigger mechanism. When the flower strikes with its reproductive hardware, the alkali bee does not retreat from the impact. It accepts the physical blow to harvest the pollen before moving immediately to the next plant in the sequence. It was the precise biological machine that the industry required for survival, but a catastrophic logistical problem remained. The species was functionally extinct within the agricultural zones of Nevada. Progress had inadvertently eliminated the very tool required for its own success. For 5 decades, heavy steel plows turned the earth while aggressive chemical applications systematically destroyed the tunnels and food sources of these insects. The camera glides along the desolate fields where we had removed the only entity capable of securing the harvest. Dr. Martinez recognized the technical irony where the answer had been present for decades, only to be buried under layers of industrial modernization. Everything only gets more complicated at this stage. To save the land, farmers would have to execute an unthinkable reversal of strategy. They would be forced to cease their struggle against the hostile environment of Nevada. Instead, the task shifted toward reconstructing the specific ecological infrastructure that had been systematically dismantled over 50 years of intensive cultivation. From here, the transformation moves to the next phase of processing as the industry attempts to restore what was lost. 100% of this initiative represents the most contradictory project in modern agriculture. Why would farmers intentionally destroy their own fertile soil to bring back a specific bee species? It would seem that a simple wooden hive would suffice for any insect. But the alkali bee requires a habitat made entirely of salt, forcing engineers to transform productive zones into artificial white deserts. This process is only gaining momentum. Technicians drive massive tractors into green fields not to plant seeds, but to systematically alter the soil composition. The engineering required for these salt beds matches the precision of heavy industrial construction. It only looks obvious to pour salt on the ground, but in reality, the process demands surgical accuracy. At first glance, the destruction of the topsoil seems chaotic, but the camera glides along the excavation site, where the earth is first removed to a specific depth. A complex network of underground irrigation pipes is installed, costing tens of thousands of dollars. One can notice how the equipment gradually buries these lines, so the water never reaches the open air. Instead, the moisture remains trapped in the subsoil, keeping it damp and soft enough for the bees to excavate their tunnels. Everything only gets more complicated. Heavy trucks discharge tons of industrial salt across the leveled earth. Laser-guided graders move back and forth to ensure the surface remains as flat as a billiard table. The salt functions not as a toxin, but as a specific technological tool. It draws moisture from the irrigation pipes below, sealing the surface into a hard crust that provides perfect thermal regulation for the larvae. To an outside observer, the site resembles a zone of total ecological failure. Neighbors frequently stop their vehicles to watch the progress and mock the effort. Local media outlets labeled the project a bizarre experiment. Farmers were investing entire fortunes to create a brilliant white dead zone in the center of their vibrant green holdings. It seemed like the absolute opposite of agricultural progress. However, this remained the only viable strategy left for pollination. The stage stood completed, reflecting the intense sunlight and waiting for its inhabitants. The process is only gaining momentum as the delivery phase begins. Specialized transport vehicles arrived at the site carrying heavy wooden crates. These containers held no electronic sensors or genetically modified seeds. Instead, they were filled with blocks of raw earth containing millions of dormant alkali bee larvae. The scene appeared anticlimactic to the skeptics, yet it was a moment of extreme tension for the investors. Workers began dumping the contents of the crates directly onto the salt crust. One can notice the complete absence of traditional wooden hives or protective netting. No apicultors in specialized suits were present during the transition to the next level. Millions of insects were simply deposited onto the hot, salty floor of the artificial desert. The internet responded with immediate ridicule. Footage of the soil being dumped went viral across social platforms, accompanied by thousands of comments mocking the perceived stupidity of the landowners. The material remains on the salt beds, beginning its slow integration into the new environment. $40,000 was the initial investment that armchair experts claimed would be lost to the scorching heat of the sun. Why did the desert surface remain eerily quiet during those first critical days? Skeptics watched the motionless white crust and predicted a total biological collapse. A single sentence of delay followed by the realization that the heat was not a destroyer, but a catalyst. The answer lies in the thermal regulation provided by the subsurface moisture, which protected the dormant life from the intense Nevada radiation. It only looks obvious that a lack of surface activity equals failure, but in reality, the investment was already transforming deep within the soil. Tension on the local farms reached a peak as the white expanse of the salt flats showed no signs of life. If the project failed, the financial ruin would be eclipsed by the weight of public humiliation. One can notice how the newspapers began printing headlines regarding the certain demise of the operation. The process is only gaining momentum. Crying failure was premature because the revolution was occurring exactly where the cameras could not reach. Centimeters below the heavy boots of the critics, a massive subterranean army was beginning to stir. Beneath that hostile crust of alkaline salt, one of the most complex biological engineering feats on the planet was currently in progress. This does not end at this stage. Alkali bees do not simply excavate random holes in the ground. They construct organized industrial cities. In the darkness, where the humidity is maintained at a perfect constant by the automated irrigation system, the insects began their labor. Each female functions as an elite biological miner. It is visible how they carve perfectly round vertical tunnels that descend 50 centimeters into the earth. The precision of the excavation is mathematical, ensuring the structural integrity of the tunnels remains intact as the colony expands. The equipment gradually stabilizes the environment while the bees reinforce the walls of their shafts. Everything only gets more complicated as the density of the tunnels increases across the field. One can notice how the insects move soil to the surface in tiny, measured increments. At first glance, the desert floor is a wasteland, but in reality, it is a high-functioning production center. This marks the conclusion of the initial nesting phase, as the biological infrastructure is now firmly established within the salt flats. Thousands of alkaline bees cement the interior walls of their tunnels, transforming them into smooth and reinforced tubes capable of resisting structural collapse. Why is the crust of salt on the surface, previously criticized by many, so vital for this architecture? This layer functions as a tactical shield. It reflects excessive thermal energy and possesses a hardness that prevents predators like beetles and ants from penetrating the interior. The salt serves as the impenetrable wall of a biological fortress. One can notice how the population density defies standard urban logic within these salty sectors. Thousands of nests operate in immediate proximity within a single square meter of ground. It is visible how this invisible, high-density metropolis expands beneath the surface. Inside each individual tunnel, the bees construct specialized brood chambers and coat them with a natural waterproof secretion. This substance protects the stored pollen and eggs with the security of a bank vault. The city grew continuously day after day. Where humans perceived only white, sterile earth, life was surging on a massive scale. Human infrastructure, including the pipes, the salt distribution, and the leveling of the terrain, served merely as the primary foundation. The bees acted as the final architects, and upon the completion of construction, the city opened its gates. The subsequent change was not a gradual shift, but a total explosion of activity. And this is not the limit. Weeks after the stabilization of the beds, the alfalfa fields surrounding the salt flats began to vibrate. A deep and constant low-frequency hum filled the atmosphere. Alkaline bees emerged by the millions, and they were not there for idle flight. The efficiency of these creatures made common honeybees appear like mere amateurs. High-speed cameras captured the mechanical brutality of their pollination process. An alkaline bee lands on the flower and applies a calculated amount of pressure to the petal. Pa! The flower triggers its internal mechanism with a sudden snap. The bee receives the physical impact directly against its thorax, collects the released pollen, and moves to the next flower in a fraction of a second. They do not hesitate or show fear. They function as biological machines programmed for this specific mechanical task. The speed of pollination doubled and then tripled across the fields. It is visible how the purple beauty of the blooms began to mither rapidly, which is the universal technical sign that successful pollination has occurred. Seed pods began to swell under the weight of the developing yield, physically bending the plant stems toward the earth. Farmers could hardly believe the visual evidence of the harvest potential. It only looks obvious in hindsight, but the transformation was absolute by the time the harvesters finally entered the fields at the end of the season. The material is ready to move to the next processing phase without haste. 1,200 kilograms per hectare is the volume farmers began harvesting in regions where the historical average previously stagnated between 300 and 400 kilograms. Why did such a drastic leap in output occur so rapidly? This massive surge represents a productivity increase of 300 to 400%. The multi-million-dollar investment directed toward the salt beds was fully recovered during the very first harvest cycle. One can notice how the calculated risk effectively outperformed conventional expectations. Nature, utilizing its ancient and uncompromising mechanics, surpassed modern chemical interventions and heavy industrial machinery by a significant margin. But this is just the beginning. Today, looking down upon the Nevada desert, certain geometric features become visible from high altitudes. Bright white squares cut through the expansive green of the cultivated fields with mathematical precision. These are not remnants of environmental damage, but rather structures reflecting technical intelligence. At first glance, industrial progress is often associated with the development of microchips, autonomous drones, or sterile laboratory environments. In this specific region, the industry encountered a fundamental lesson in technical humility. It only looks obvious that the path forward requires new inventions, but in reality, a leap into the future sometimes demands the courage to examine primitive solutions. The process is only gaining momentum. It requires the audacity to introduce salt into fertile earth, relying on a biological design refined by millions of years of natural field testing. The equipment gradually integrates with these natural cycles. Nature does not require the reinvention of the wheel, but rather the return of the ecological balance that was previously disrupted. The financial results from millions of dollars in surplus seed production confirm the success of the methodology. Everything only gets more complicated as global supply chains come into focus. 8 out of every 10 oysters served in high-end establishments from Paris to New York originate from a single nation. This fact remains hidden behind the luxury of the product. But behind this specific delicacy lies a technical challenge involving toxic waste. White mountains of discarded shells accumulate and resist natural decomposition. In China, these massive ridges of calcium-rich waste rot in the open air, discharging gases that contaminate the surrounding atmosphere. The camera glides along these structures where the scale of the accumulation is visible. The process reaches a critical paradox at this stage. This hazardous waste represents the only viable treatment for agricultural soil that is currently dying from extreme acidity, reaching levels comparable to lemon juice. Transition to the next level of processing involves neutralizing this imbalance. One can notice how the transformation of an environmental catastrophe into white gold begins to take shape. The machinery for processing these mountains of shells must now operate with high efficiency to reclaim the land. The material is prepared for the next phase of its industrial transformation. 11,200 kilometers of coastline define the maritime borders of China, a massive expanse that has been reconfigured into the largest ocean protein factory on the planet. Why does the scale of this production create an unprecedented environmental challenge for the region? This output is not merely a matter of industrial pride, but a necessity of global demand. In the span of just one single year, this nation generates an astounding 11,900,000 tons of oysters. This is a quantity of food that remains difficult to visualize through simple observation. The equipment and labor involved in this harvest surpass the combined seafood production of industrial giants like the United States of America, Japan, and France. But this is just the beginning of a complex biological crisis. At first glance, the harvest seems like a triumph of food security. But in reality, the uncompromising biology of the oyster dictates a massive logistical failure. Only 10% of the organism consists of edible meat, while the remaining 90% is a rigid armor of calcium carbonate. One can notice how this material remains as hard as stone, resisting natural decay for several centuries. Everything only gets more complicated as the harvest cycles repeat. 6,600,000 pounds of shells are discarded every single year into the local environment. These structures do not simply vanish into the earth, but instead accumulate in permanent layers. Along the coastal beaches of Fujian and Guangdong provinces, the landscape has been physically altered by the emergence of new geological formations. These are artificial mountains of white shells reaching several meters in height. It is visible how the equipment gradually piles these remnants into vast ridges that dominate the shoreline. The process is only gaining momentum as the temperature rises. Under the humid and heavy heat of the summer months, these massive mounds transform into active chemical reactors of organic decomposition. Small fragments of residual meat trapped within the narrow crevices begin to rot, triggering the rapid proliferation of bacterial colonies. This biological breakdown releases invisible clouds of ammonia and hydrogen sulfide into the atmosphere. the air becomes physically toxic, causing immediate irritation to the lungs of local residents who live near these sites. Transition to the next level of destruction occurs when rainwater washes these substances into nearby bodies of water. The chemical runoff strips oxygen from the lakes, leading to the mass death of fish populations and the collapse of local ecosystems. The weight of these shells creates a pressure that alters the very soil beneath them. From here, the transformation moves to the next phase of processing as the environment struggles to absorb the industrial waste. 3 8/10 to 4 2/10 is the critical range of soil acidity currently recorded throughout the Fujian region. Why has the fertile ground reached such a state of total exhaustion? Although an excess of materials exists nearby, the local orchards presented a scene of absolute desolation as recently as 2021. The soil is dry, cracked, and completely devoid of life, reaching acidity levels comparable to pure lemon juice. At first glance, the terrain looks like ordinary farmland, but in reality, the earth has become an environment so hostile that tree roots burn upon contact and lose their grip entirely. When rainfall occurs, the water fails to penetrate the surface. Instead, it flows away across a ground that has become hard and impermeable, behaving much like wet cement. It is visible how the lack of absorption prevents any nourishment from reaching the deeper layers. Everything only gets more complicated as the timeline for total collapse approaches. Local authorities have officially acknowledged a terrifying reality regarding the future of these agricultural zones. If no intervention is implemented, vast areas of cultivated land will be abandoned in less than 15 years. On one side of the region, mountains of calcium waste accumulate and contaminate the air, while on the other, acidic lands suffer from a desperate lack of that very same mineral. It seems simple to connect these two disasters, but the solution required colossal engineering. The answer did not emerge from a futuristic invention, but from the large-scale industrialization of an ancient concept. Engineers realized that those mounds of foul-smelling waste were actually mines of pure biological limestone. But this is just the beginning. To transform toxic residues into a remedy for the earth, a massive machine had to be constructed. In Ruyan, a factory of enormous proportions was established with a single objective: to devour 264 million pounds of oyster shells every single year. The equipment gradually processes the waste using a combination of brute force and thermal precision. One can notice the massive scale of the operation as heavy trucks discharge raw shells into industrial crushers. The process is only gaining momentum. These crushers break down the initial limestone structure into smaller fragments. But the true secret of the transformation lies in the fire. The camera glides along the automated line where the crushed shells are fed into gigantic rotary kilns for a process known as calcination. Inside these massive rotating cylinders, the temperature rises steadily until it reaches 473 degrees. The shell fragments tumble through the heat as the material is chemically altered. Transition to the next level. This thermal treatment ensures the final product is ready to stabilize the dying soil of the region. 245 degrees Celsius is the constant temperature maintained inside the industrial kilns. For 30 minutes, the oyster shells undergo baking within this strictly controlled environment. Why is such intense heat necessary for processing marine waste? It only looks obvious that the shells need drying, but in reality, the thermal treatment serves two critical functions at once. The first purpose is absolute sterilization, where any harmful bacteria or decomposing organic residues are incinerated instantly by the high temperature. The second function of the heat is the fundamental alteration of the physical structure of the shells. One can notice how the solid calcium carbonate becomes brittle and extremely easy to grind into a fine consistency. It gets more complex further on. What emerges from the other side of the production line is an exceptionally fine white powder identified as oceanic biocalcium. This substance is far more than simple crushed stone, as it functions as a specialized soil conditioner saturated with essential minerals that the depleted lands of Fujian lost many decades ago. The chemical composition acts as a natural antacid for the earth. Imagine acidic soil behaving like a human stomach suffering from heartburn. The biocalcium neutralizes this acidity immediately upon contact with the ground. This reaction unlocks vital nutrients that were previously chemically trapped and creates an environment where biological life can begin to flourish once again. At first glance, the piles of shells were merely toxic waste, but the process is only gaining momentum. 220 million pounds of clean, high-grade agricultural product now sit in heavy bags, ready to restore local harvests. The equipment gradually fills these containers for transport across the region. Although the theoretical model for this restoration was perfect, industrial agriculture remains an unpredictable field of battle. The process does not end at this stage. The real test for the material began at the moment the heavily loaded trucks arrived at the devastated farm territories. One can notice the dust settling as the first batches are spread across the fields. The technical results were immediate and visible, confirming the effectiveness of the mineral transformation. 60% is the staggering increase in yield recorded during the initial large-scale success with scallion cultivation, a crop of vital importance for the regional economy. In agricultural fields where vegetation had previously turned yellow and remained stunted, the systematic application of the processed shell powder triggered a complete biological resurrection. One can notice how the plants regain their structural integrity as the productivity spike allows for the generation of 60% more food from the exact same surface area without the introduction of supplementary chemical fertilizers. Why did the scallion crops undergo such a drastic transformation? It seems simple to attribute this to luck, but in reality, the crushed calcium carbonate neutralizes soil toxicity at a cellular level. This allows the root systems to absorb nutrients that were previously locked away by high acidity. In the grapefruit orchards, the recorded changes were both chemical and profound. Digital sensors buried deep within the earth indicated that the pH level rose by 1.1 points, effectively moving the soil out of the hazardous acidic zone. The organic matter, which serves as the fundamental fuel for subterranean life, increased by nearly 28%. One can notice how the trees cease the premature dropping of fruit, while the foliage returns to a vibrant, healthy green hue. But this is just the beginning. The victory extended beyond the physical condition of the land to the financial stability of the local farmers. An experimental study involving lettuce crops revealed technical results that were highly unexpected. The plants cultivated with the fine shell powder did not merely grow larger in physical volume, they became objectively more flavorful. The process is only gaining momentum. Laboratory analysis confirmed that this lettuce was crunchier, sweeter, and significantly richer in vitamin C compared to specimens grown using traditional synthetic chemicals. The wholesale market responded immediately to these superior physical characteristics, and the price of the produce rose by between 12 and 18%. For 300,000 rural families, this transition represented a genuine economic revolution rather than a simple technical adjustment. It is visible how the cycle reached a state of functional perfection as the equipment processed the marine waste into a resource. The discarded remains from the sea saved the productivity of the land, and in turn, the land rewarded the labor of man with higher quality yields. Everything only gets more complicated further on. However, the equilibrium of nature does not always remain static. The material is ready to move to the next processing phase without haste. 37,500 million pounds of peanuts are harvested every year in China, making the nation the largest producer of this global commodity. Why did the application of the miracle powder on degraded peanut fields result in a frustrating mystery instead of a triumph? At first glance, the chemical restoration was a success as the soil pH levels rose and the earth became noticeably softer and less compacted. However, despite these physical improvements, the total harvest weight unexpectedly began to decrease. One can notice how the equipment recorded a decline in yield where an increase was predicted. Peanuts are a strategic crop and a member of the legume family, which means they rely on a complex symbiotic partnership with specific bacteria inhabiting their root systems to capture nitrogen directly from the atmosphere. The answer lay hidden within the microscopic world of soil biology. A rapid shift in the acidity of the earth, triggered by the sudden introduction of oyster powder, delivered a fatal shock to these sensitive microbial colonies. They simply could not adapt to the high velocity of human intervention. It was a brutal lesson in technical humility for the field engineers. The ecosystem requires a specific duration to recalibrate its internal balance. It is visible how the biological processes lag behind the chemical changes. But this is just the beginning. Engineering cannot rush biology, as the oyster powder proved it was not an instant solution for every plant species. While scientists learned the necessity of patience on land, another specialized team redirected their focus back toward the ocean. The crisis was not limited to the mountains of shells accumulating on the shore, but extended deep beneath the surface of the water. Over the last 150 years, 85% of the natural oyster reefs in the region had vanished entirely. The seabed, which once functioned as a dense and vibrant forest, had been reduced to a barren desert of mud. It gets more complex further on. Restoring this lost underwater world did not require high-technology solutions, but rather the application of ancient wisdom. Engineers and biologists bypassed modern concrete and complex metal structures to adopt a method dating back 300 years. They utilized simple stakes made of bamboo and timber, driven manually into the coastal mudflats with rhythmic precision. The camera glides along the rows of wood protruding from the silt. This objective was to provide a stable foundation for free-floating oyster larvae to attach themselves to. The process is only gaining momentum. No heavy machinery was deployed in this zone, as workers relied only on timber and the natural power of the tides. The resulting explosion of life left the technical experts astonished by the sheer scale of the recovery. Within a few months, the stakes were completely encased in layers of new oysters. The total biomass in the treated area increased 10 times over its previous state. But the true power of these artificial reefs is not found in providing a habitat alone. Everything only gets more complicated. One can notice the water clarity improving as the biological filtration machines begin their work. A single adult oyster functions as a specialized biological engine capable of processing vast volumes of liquid every hour. The molten stream of ecological restoration goes further along the production chain.